Hello. So, um, uh, yesterday, I think it was yesterday, I did a short video on the moon shadow, and I knew what was going to happen next. I knew exactly the kind of things that would come up. So today, when I got home, I did the Supergeek version of the moon shadow with maths and physics to prove that what I showed yesterday in the short video about the moon shadow is true, holds water, and so on. I did it for a couple of reasons. One is I knew quite a few people would say, oh, but the Kurgan doesn't understand. The moon has got the same size as the sun because they're so far apart, so the light doesn't actually make a cone. No, it does make a cone, and you don't understand basic math. So that was one reason. The other reason is that I just wanted to test it for myself. So when I did this, I went online to get the distances of, the as exact as I could get the distances of the diameter of the moon, the diameter of the earth, the diameter of the sun, the distance from the moon to the earth, the distance from the earth to the sun, and so on. But what I didn't do is look up what the diameter of the moon shadow on earth is when there is a full solar eclipse, which is when the moon passes in front of the sun and creates a shadow on earth that we see as an eclipse. So when the video that I did yesterday is like 6 minutes long, so go look at it if you haven't seen it first. But I wanted to prove to myself whether the numbers added up and whether the hard shadow is said to be about 70 miles across, which is about roughly just over 100 kilometers across. So I thought, no, I'm going to do the maths myself and see if I come up with the same number. So that was one reason. In doing this exercise, I also became aware of something else that's very important, which is that I expect most adults to have a basic understanding of maths that I did at elementary school, trigonometry and so on, algebra and so on. But the reality is that in the modern world, probably a vast majority of people and almost all the millennials don't know how to do this maths. And that's not their fault. If nobody's shown you something and you don't know how to do it, that's understandable. And it's quite a realization for me, because a lot of the times I get irritated with people, it's because I think, well, you know this, so why are you being such a dick? But the fact is they don't know that. They look like adults, they walk like adults, they talk like adults. But the reality is really, at many, many levels, they're children, and that's, again, not their fault. So, if you've been watching my videos by now, you know I'm a very high-tech guy, so you're gonna have to excuse the camera work a little bit as I turn this around and look at the computer screen next, which is what we're gonna do in a moment. So let's first get up the where is it? There we go. Right, now I'm gonna turn this around and let's just, like I said, bear with me. You can tell that my tech skills are brilliant as always. Right, let's get this as close as we can. And don't worry, I'll be zooming in so you'll be able to read all that stuff, but I just want you to get a feel for the whole thing. There we go. It's about right there, roughly. Okay. So I'm just gonna lock this down. So what I did is I worked it out with all the maths, and I will also show you the calculations later. But in essence, and like I said, just bear with me. The camera work is gonna suck a bit, but so this is a full-size scale of the sun to the Earth-Moon distance and the light angle. Now this has been drawn to scale on a program that I've had for a couple of years called Bluebeam, which is not ideal, okay? What you'd really want to use is something like CAD, but I don't have that. I've just got this, and it's pretty much at the limit of what this program can do. So this distance is 150 million kilometers, also known as 1 astronomical unit. And this is the distance between the Sun and the Earth. Now, I'd like you to point to see, that's the Sun over there, and that's telling you its diameter, and that is telling you its radius. I will zoom in a second, but I just want you to get a sense of the scale, right? That's all drawn to scale, and this is how far the Earth and the Moon are. Do you see those two little lines? That's the Moon, that's the Earth, and we'll zoom into that in a minute as well. So let me just zoom in here first and get you to see what I'm talking about. So notice how much I have to zoom in, and I'm sorry this is not a smooth transition, but it is what it is. You don't come here because of my video skills, you come here because of my brain. So that 1.392 million kilometers is the diameter of the Sun, and that's the radius, just in case you wanted to know that. Now notice that light goes off from the Sun in every direction, of course, but the points that interest us is the uppermost point and the lowermost point, because some light from this region is going in a straight line towards Earth and the Moon. So let's go across and see where that is. I don't know if you can see the faint lines, and I'm continually scrolling right now. This is how long it's taking. There's the halfway mark, right? That's 1 astronomical unit telling you. And if you can see these two lines here, they're getting closer and closer together the further out we go. Now, because, like I said, this is at the limit of what this program can do, you will notice that, and I think this is as zoomed in as I can get on this program, yeah. So sorry, but I don't think, I'm not sure that I can get any bigger, right. So the distance here between the Moon and the Earth is correct. So this is to scale, it's roughly 400,000 kilometers. It's not exact because it's really difficult to get the things, but this is just to show you, this is not really important, it's just to give you a sense of things. And these numbers are completely out. The diameter of the Earth is only about 12,700 kilometers, so this is more than double the size of the Earth, and that is to scale. So that dot is twice what it should be. And the Moon is way out, because the Moon should only be about 3,700 and change in terms of kilometers, in terms of diameter, and I've got it as 17,000. That's as small as I could go so that you could still see a dot. So the scale here is wrong, but it gives you a sense, right? I mean, that dot should be less than half the size, and this dot over here should be something like about almost 1/5 of the size, okay? So what does this all mean? Well, how do we work out? Can you see though that the light from the Sun is a very thin wedge here by now? Because remember, that line there is the top line, that line there is the bottom line, that's from the top of the Sun, that's from the bottom of the Sun. They make a thin wedge. Now, because the scale here is so big, you will notice I did something else below it, which will take you to now. And what I did below is I enlarged just this part, just these two little lines between the Moon and the Earth. I enlarged it and drew it again over here. So that distance, and this is more accurate because the scale is a little bit bigger now. So I'm going to show you that next. And sorry, yeah, this is upside down, but it is, like I said, it is what it is. I did this when I got home in a half hour or something. So that, although it's upside down, is the correct distance between the center of the Earth and the center of the Moon. Again, to give you a sense of scale, that is now the correct diameter of the Moon. It's out by like about 20 kilometers, but at this scale, so it really doesn't make any difference. that is pretty much correct size of the moon at this scale, and this is how far away the Earth is, and there is the Earth also correct to scale. Okay, now what you have to keep in mind is that you've got the light from the sun hitting the top of the moon and making a wedge that eventually projects onto the Earth. And that's why it's only 70 kilometers across. So let me show you how we figured this out. We know the distance between the center of the sun and the center of the Earth. We also know the distance between the center of the moon and the center of the Earth. So we've got all these distances. Now we have to use a little bit of trigonometry to figure it out. And this is where I hope to educate those of you who haven't got a clue what trigonometry is. Don't get scared, just keep paying attention. If you don't know what trigonometry is, don't worry about it, I will explain it. Now, what this line here represents is the diameter of the moon. What this line here represents is the beam of light from the sun that's just going past the top of the moon. And this line here represents the beam from the sun that's going past the bottom of the moon. You'll see they have a slight angle. In other words, this angle here is not 90 degrees. In fact, this angle here is 89.73 degrees. That's what the angle here is. And we know this, we've worked it out using trigonometry because we know the distance between the sun and the Earth. We know the diameter of the sun, so we've got a triangle. We've got a triangle that goes from, or actually we've got a trapezium. We've got a trapezium that goes from the diameter of the sun all the way to the other side to the diameter of the moon. So we know the length between the top of the sun and the bottom of the sun. That gives us the base of the trapezium. We know the distance from the center of the sun to the center of the moon. So we've got that distance. And that means that we've now got a shape that has this shape here. It's the same shape. Okay, so originally we worked out what this angle is using trigonometry, and I'll get to the maths later, okay? And now we want to figure out, this is in this area here, inside this shape, that's shadow. Okay, outside you've got light. So the shadow you can see is becoming smaller and smaller and smaller. And at this point is where it hits the Earth. Now, we don't know, right, what that diameter is. That's what we're trying to figure out. But we do know what the angle here is. And we do know what the angle here is. And we also know that this is the moon's diameter, okay? We don't know what this length is from there to here, but we know this length here, the moon's diameter. So because we have this angle, and because we also have this length, because this length here is the distance between the surface of the Earth and the center of the moon, okay? This line is the diameter of the Earth. And that's fine for our purposes. The distance, we don't have to take it from the surface of the moon because there would be an arc here like that, but we don't have to take it from the surface of the moon. It doesn't matter because the sunlight gets past the moon here at the very top of the moon and at the very bottom of the moon. So the center of the moon is fine. We know that's a 90-degree angle. We know that angle, and we know this distance, okay? Because this distance is the distance which is from the center of the moon to the center of the Earth minus the radius of the Earth. Because keep in mind, what this here is showing is just the surface of the Earth. The Earth is much bigger and it keeps going around. And the distance between the moon and the Earth is measured from the center of the Earth, which would be somewhere around here, to the center of the moon. So we have to subtract the radius of the Earth to get to the surface of the Earth. Now you're saying, oh, but there's a curvature. Yes, there is, and it doesn't matter. Okay, it doesn't matter about the curvature because the difference is going to be less than a kilometer over over 100 kilometers, the difference of the curve is going to be less than a kilometer. And we're using such big numbers that it really makes no difference at all. So because we have this angle and we have this line here, which is known as the adjacent, this line would be known as the opposite, and this line here is the hypotenuse of the triangle. It's just a name, okay? The longest side of a right angle triangle is known as the hypotenuse. The short side is known as the opposite, and the medium sized side is called the adjacent. Now, using a formula of trigonometry where you have the tangent of the angle, the tangent is just a function. You can press it on your calculator, okay? I'm not going to bother explaining how that works and whatever. It's not important. All you need to know is that if you have an angle, every angle has a tangent. So you know this angle is 0.2666 blah 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 degrees. You type that into your calculator, you press the tan function, and that gives you the tangent of that angle. Now, what is the tangent? The tangent is the opposite divided by the adjacent. So because we know what the adjacent is, and because we can get the tangent of that tiny angle, all we need to do is get the tangent of the tiny angle and multiply it by this distance here, which is the green line, and you will get this distance here. Why is that important? Because that distance there is the top of the moon's shadow on the Earth. So, and it's going to be the same at the bottom. So all you've got to do now is you've got the diameter of the moon, you subtract this distance, and the same at the bottom, which is going to be the same distance. So this distance multiplied by 2, you subtract that from the total of the moon. And guess what the number that we get is? The number that we get is the diameter of the shadow on Earth. Now, I intentionally did not check to see what that number would be. And what I came up with in my calculations is that the biggest number that you would get here is 156 kilometers. That's important because the moon is not always at the same distance from the Earth. So at its closest point, when the moon is closest to the Earth, this distance, by my calculations, is 156 kilometers. When the moon is furthest away from the Earth, you won't get a shadow at all, because these two lines will meet. They will bump into each other somewhere, say over here, and the Earth is even further away. So you don't get an eclipse. You don't get a hard shadow on the Earth at all. Keep in mind, however, that above here and below here, you still get what is known as the penumbra. This is known as the umbra, the dark part of the shadow. The penumbra is a partial shadow, which means you see a partial eclipse, which is why, it's also why the moon wanes and waxes and wanes and so on, because our shadow reflects on the moon in similar sort of ways. Anyway, that's basically it. Now, I don't know if you guys want to see the maths, but why not? Let's just have a look. Here we go. I don't know if you can actually see that, but here you've got the base of the trapezoid, which is the sun's diameter, 1.392 million kilometers. This is the top of the trapezoid, which is the diameter of the moon. Then you've got, this is how we worked out the angles, right? Because half of the diameter of the sun less half of the diameter of the moon will give you the base of the triangle, which is that. We know the distance from the sun to the center of the Earth, and we know the distance from the Earth to the center of the moon. So we take the distance from the sun to the Earth, and then we take away the distance between the Earth and the moon, and you've got the distance between the sun and the moon, which is that. So we've got the base of the triangle, we've got the adjacent line of the triangle, and we work out the hypotenuse, which is that number over there, which is a little bit bigger, as you can see, of the other one. So we know it's got a 90-degree angle, and we can find out what the other degrees are by using the sine function and the cosine function to get the angles. That's where the angle that I showed you before, that's where they come from. These angles are going to stay the same for the next trapezium, which is the one that I discussed just now, where you've got the diameter of the moon and the sunlight hitting the earth, and you've got the base of the trapezoid is the diameter of the moon, and the top of the trapezoid is the diameter of the shadow that the moon casts on the earth. And you'll see here that according to my calculations, this is just more calculations. It's the same, using the same stuff. And you'll notice that I've got here, I'm gonna try and zoom in. Maybe you can see it better if, let's see, 150, maybe you can read it. I hope you know, maybe not, maybe 200. Let's try that. Yeah, you should be able to read that. So diameter of the moon less 2 times the opposite side, blah, blah. Okay, this is just the explanation, okay? But what I wanted to show you is this is the diameter of the dark shadow. That number there is 156.5 something kilometers. That's in kilometers. So that's the biggest the diameter of the moon ever gets. And this is the smallest that it gets when the moon is the furthest away. And here are the distances, okay? So that is the distance when the moon is closest to the earth, and that's the distance when the moon is furthest away. You'll notice that when the moon is furthest away, the shadow on the earth is minus 310 kilometers, meaning that there is no umbra, there is no hard shadow. And when it's closest, it's 156 kilometers. And that's how, that's what I figured out using the numbers that I did. And then I went to check, only after I did all this, what actually is the size of the shadow on Earth. And it's given as 150 kilometers. Now the fact that I'm out by 6 kilometers, considering that the distances involved are 150 million kilometers basically, that's a tiny error. So that proves it beyond any shadow of a doubt that is the maximum size of the umbra, or the shadow, the hard shadow that the moon can cast on Earth, okay? And there we have it, ladies and gentlemen. So I am now going to, let's see if I can turn this around again and still get myself in the frame. I don't know if I'll be able to do that. Let's see. Sort of, but not really. Let's see. I have to just bear with me 1 second. If you suffer from motion sickness, this will be the time to look away. Let's see now. That's a bit better. Okay. Yeah, of course, if my tripod locked, that would be better. All right, so that's basically it. So that was the Supergeek version, and again, as you all know, I'm very technically minded, so if I figure out how, I might just put the proof and the documents on the blog, but I don't know if that'll allow you to download them or not. I'm not sure how to do that. I'll have to think about it. But there it is. Now there was 2 guys that left some comments which are still on the YouTube video. One was Tinfoil Fan, I think. So Tinfoil Fan was one of the guys that said, "Oh, Kurgan, I think you're wrong because the moon and the sun are the same size because of the distance involved." No, it doesn't matter what the distance involved is. they're not the same size. They are not the same size. So the light from the top of the sun that hits the top of the moon and the light from the bottom of the sun that hits the bottom of the moon are coming in at an angle, and they will form a cone. And what I've shown you on that paper is all drawn to scale. Don't take my word for it. Do it yourself. Figure it out. You can find all the distances online, and you just need basic trigonometry, which is something, I was doing that in elementary school. I wasn't in high school when I was doing trigonometry. So I know that it's not your fault. I know that if you don't know what trigonometry is, if you haven't got a clue about what a sine, cosine, and tangents are, if you don't know the famous SOHCAHTOA, the sine is equal to the opposite over the hypotenuse, the cosine is equal to the adjacent over the hypotenuse, and the tangent is equal to the opposite over the adjacent. If you don't know that, if you never got taught that, that's not your fault. But you can find the stuff online. It's not hard. If you don't know how to do trigonometry, spend 15 minutes, go online, figure it out. It's worth it. It's useful. I didn't have to Google how to do trigonometry. I had to Google the distances because I wanted to get the precise distances. I knew them roughly, I know that it's roughly 400,000 kilometers to the moon. I know that it's roughly 150 million kilometers to the sun. I know that the sun is about 1.3, 1.4 million kilometers across. I know the diameter of the Earth is about almost 12,800, not quite kilometers. I know the diameter of the moon is 3,700 and change kilometers. So I know that stuff, but I wanted to get as precise a number as I could. And that meant going online to get it just because it's faster. I used to do the stuff for fun when there was no internet, and I used to have to go in a book to find it all out and work it out by hand, So trust me, you can do it. You can do trigonometry. It's not that difficult. And it'll prove to you for yourself that, the stuff works, that it works, that it's true, that, there is a smaller hard shadow. And, to the guy who said, oh, but the overall shadow is never smaller. Yeah, it isn't. The overall shadow can be bigger. Of course, that's fine, because keep in mind, the same light from the top of the sun that's hitting the top of the moon is also hitting the bottom of the moon. And so it's creating, two cones, an inverted cone that keeps getting smaller, which is the hard shadow known as the umbra, and a bigger cone, a reversed, which is getting bigger rather than smaller, which is the penumbra, and it's not hard shadow, it's like, partial shadow. So that's it. That's about it. I've got another announcement, another little video I want to do tomorrow, but I've got a new book out, and I'll talk to you a little bit about that. It's just a little bit controversial, and it's called Believe. So if you want to rush and get it first, go for it. It's on Amazon already, both in hardback and hardcover. It's not hardcover, it's paperback. But 3 version in paper and on Kindle. If you get the paper version, you can get the Kindle one for like $1.99, I think. If you are an agnostic, if you are an atheist, if you are some kind of pagan, if you're a bit of a churchian, or even if you're a Christian, I strongly suggest you buy that book, especially if you're a little bit of a wild animal. I wrote that book specifically for people that would have been very resistant to Christianity, such as myself, who lived like a wild savage for many, many years. So, and it's not written like any kind of theology book you've ever read before. A friend that gave me a review for it, he's the guy that wrote Safe Space as Rape Room for the Castella House blog, which was Hugo nominated as part of the Rabbit Puppy campaign. Anyway, Daniel Ennis, who's the guy who wrote that, and he did a brilliant piece of work on that. He exposed the pedophilia that is present in the science fiction writers of America. But he gave me a brilliant review, which ended off with something like, we have now finally, Mr. Filotto has now demonstrated a a role-playing game character class that we've all been missing, the theologian berserker. So you'll understand when you read the book, it doesn't pull any punches. So there you go. If you want to jump the gun on it, you can go and get it. But I'll talk about it a bit more and explain, what it's about and what's in there and why I think it'll be useful, especially for young guys and especially for people who are resistant to Christianity because of all the pedophilia in the Catholic Church, because of all the bullshit, lies, theft, money-hungry, money-grabbing, power-grabbing scumbags that pretend to be Christians but really are just church and, if not satanic, predatory child molesters. So yeah, anyway, that's it for tonight. Good night. And now I'm gonna see if I can find the off button while not really being able to see it.